Good afternoon, everyone. Thank you, Andre, for the introduction. And Ben is here as well, so please welcome Ben Bloom from Atom Computing, the CEO and founder of Atom. So we're thrilled today to be sharing that we now have a partnership with Atom Computing to bring neutral atom capabilities to our Azure Quantum Compute platform. And also we are offering a commercial offering, which we like to call a discovery suite. And I'd like to, let's see if that is not the same. One moment. We also offer a discovery suite, which brings together HPC, AI, and reliable quantum computing. So lighting up logical qubits, co-designing the system with Atom Computing and Microsoft together to bring forward a reliable quantum machine that will integrate alongside HPC and AI. And so it's really about applications, right? These next generation applications require a hybrid workload. And so this hybrid workload has across it, right, AI at scale, reliable quantum computing, and HPC, right? So you need to bring together the scale of HPC, the ability to automate across many capabilities in the cloud. You then use the reliable quantum computer essentially as an accelerator to that CPU and GPU capability, right? So you have certain capabilities that you deploy on the quantum machine for high accuracy results, for example, in energy estimation. And then you can take data from the quantum machine and train an AI model, right? And then use this AI model to predict or estimate different quantum properties. So this is really the view of what a modern hybrid application looks like. Now, behind all of this, we have a platform, right? So this platform here is Azure Quantum, and the Azure Quantum platform brings together all of these capabilities. So it makes a seamless integration across HPC, quantum, and AI. For example, the ability to connect with Azure Quantum Elements, which is our platform for scientific discovery for chemistry and material science. And we've announced this morning that we have an end-to-end demonstration that employs Azure Elements along with reliable quantum computing and AI together. First end-to-end demonstration for a real chemistry problem. We have a paper that posted to the archive last night on that. You can read more. What I'm really excited about within the Azure Quantum environment is this Azure Quantum Compute platform, where we are announcing today that Atom Computing is joining in this compute platform, and it's really about the virtualization, right? Qubit virtualization, meaning that we are taking pools of physical qubits, orchestrating across them, bringing them to life then as logical qubits, right? And these logical qubits enable you to have more and better computation than you can do on physical qubits alone, right? And so it's really about graduating, right, from the physical qubit realm, right, the noisy intermediate scale quantum computing we have, graduating to logical qubits. We like to call this as graduating to level 2, right? Level 2 is about resilient quantum computing. Resilience meaning you can perform longer computations reliably. You need logical qubits, right? For the kind of computation we want and the types of solutions we want from quantum computers, you have to have logical qubits. So it's about advancing from 50 logical qubits onto 100. At 50, you are beyond what you can classically simulate, right? So you're doing things you cannot do classically, but it's at 100 where you achieve scientific quantum advantage. So for problems in quantum magnets, materials models, you're getting solutions when you have that quantum, that reliable quantum machine, 100 logical qubits and up. When you have that integrated with HPC and AI, you're getting solutions you can't otherwise get classically alone. And so it's with, for example, Atom Computing that we'll light up those logical qubits, and we have a roadmap that takes us together to 50 and then on to 100 and beyond. And then ultimately you want to reach scale, and this is where you'll have industrial level solutions in chemistry, for example, ability to study catalysis problems, right? Understand reaction rates to a higher accuracy, the active spaces there, understand them to high accuracy, use that data to train further AI models, and you're really at scale at that time. So it's all about the logical qubits. And You know, as was mentioned this morning in our keynote session, we announced today that we do have logical qubits with Atom computing together between Microsoft and Atom. We have these logical qubits, we've generated the logical qubits, and we're now lighting up and scaling up to 50 logical qubits and beyond. And Ben will share more there on the underlying hardware attributes that are key here in this neutral atom system. But just to give you a little bit of a visual on how we do this, right, when we look together to upgrade that system and enable it to bring to life more and more logical qubits that get better and better, this is a bit of a visual, right? We together are optimizing a mixture of the quantum error correction capabilities and the hardware attributes or features, if you will, right? Really engineering and designing together the architecture as well as the qubit virtualization so that we are able to light up logical qubits and lots of them, right? So the idea that you have movement here, this gives you access to more efficient error correcting codes, more, better capabilities to bring more logical qubits forward faster, right? So we really want to accelerate to that point of scientific quantum advantage and beyond and do that together. So I'd like to hand over to Ben Bloom, who is the CEO and founder of Atom Computing. We're thrilled about the partnership together, and he'll tell you more about the hardware side of this capability.
Thanks, Krysta. So I want to tell you a little bit about Atom Computing and a little bit more about our technology. Atom Computing is a company in Boulder, Colorado, with a branch in Berkeley, California. We have about 65 or so people, and we build nuclear spin qubits. So we build neutral atom systems that use the nuclear spin of the atom, and that qubit itself is very, very coherent. And we build these systems to really large scales, having published a system with over 1,000 qubits, almost 1,200 qubits, actually. Now, one of the amazing things that we've done with Microsoft is enabled all-to-all connectivity in that system, so move those atoms around and run circuits where we can have very, very dense connectivity. And in addition to that, we're also focused on scaling. So not only did our first generation system have about 100 or so qubits, and our second generation system can now get to about 1,200 or so atoms, we really want to make sure we stay on that path. And the next time we now co-design a system, co-design it for 10,000 atoms. This architecture obviously is now optimized for quantum error correction. And one of the things you'll see is that we have a way of actually performing measurements and keeping the system going. Now, if we dive into what that system actually looks like, it looks a whole lot like a trapped ion system, but instead of building chips, we actually create traps made of light. So inside that vacuum chamber is essentially a whole lot of nothing, but we project into it traps, and those are the traps we actually put the atoms into. We can do a funny trick where we can load a small, tiny subset, maybe 20 or 30 atoms at a time, and then build up to incredibly, incredibly large arrays. And this one, it's over 1,200, potentially, I think this is 1,225 or so. Now, that's just the systems we've already built. And now we want to talk about what we're going to build together. So right now, we have 1,000 qubits after our first 100 qubit system. We want to turn that into 50 logical qubits. And then using the amazing Microsoft quantum error correction, we want to build a 10,000 qubit system that's built entirely around running that quantum error correction natively. That system, we believe, will get over 100 logical qubits. And from there, we think we can do another level of scaling that gets us to a module size of 100,000 atoms or 100,000 qubits. And this is the roadmap we see as being able to create a module that is fundamentally useful, a module that people want to essentially get to that industrial scale problems. So with that, we can talk a little bit.
Yeah, are we able to open up for questions? I know we have a few minutes left. Yeah, Andre? Yeah. So we have some time for questions. Any questions? We're really thrilled. As you just saw, we have a roadmap together out to that 100 logical qubits and beyond, and it's really a matter of co-designing the system for scale. Yes?
Okay. Given the I/O, I can just shout. Given the I/O limitations of quantum computing for the near future, digital in, digital out, can you give some more details, whatever you're allowed to say, on where is the advantage for quantum machine learning
Yeah, so let's dive into, what does it mean here when we say quantum for AI? It's different than quantum AI, right? So I think this nuance really matters, right? When we look at actually training a model on a quantum machine, this is expensive, right? If you're having to load large amounts of classical data, that machine has to be extremely large to handle this. And when I say extremely large, well beyond the numbers we have here on, on the roadmap. So, the approach that we believe is the right direction when we think about enhancing AI with quantum computing, right? We think about using the quantum machine really as a data generator, right? The quantum machine gives you access to data you don't otherwise have classically, right? You can simulate and prepare, for example, a quantum state on the quantum machine. You can sample that state, right, measure, and use these samples then. They become classical bits, right? These classical bits become data that you can then use to either continuously train or train a new model in the AI space, right? So it's really about using this data alongside classical data and training AI models there, right? So instead of thinking of training or performing even the inference on the quantum machine itself, think about using logical qubits, reliable quantum computation to generate very accurate, right? Very clean, accurate data that you cannot generate classically, right? And then consume this data in an AI model training loop. And then you have a classical model from which you can drive the inference, right? And so that model can be fast as well and easily deployable in many, many scenarios, of course. So that's the version of bringing AI and quantum together. Then, of course, to identify where you might want to use the quantum machine, right, for which quantum subroutines, you can use the HPC capabilities, right? For example, to do massive exploration of a reaction network. You need the scale of cloud to do that. We have demonstrated the first ever on record automated reaction network exploration in the cloud with something called Azure Quantum Elements, and underneath that with something called AutoRxN. And then using a tool called AutoCast within Azure Quantum Elements, we're able to identify the active spaces that have strongly correlated electrons. So I hope that answers your question. Do we have time? I think we have time for one more. We have 2 more minutes. One more? Yes. If there is one more. Great, one at top.
Excuse me. I got a question. For the roadmap, there was no specific timeline for it. Is there any timeline for the roadmap?
Yeah, I can tell you a little bit about that if I bring it back up. So when we built our first generation system, we had it up and running in about 2020 or so. And to build our next generation 1,000 qubit system, it took a little over 2.5 years. So we imagine that it takes about 2.5 to 3 years every time we're building a new generation of system.
All right, with that, thank you so much. We're thrilled about the partnership again between Microsoft and Atom Computing, and about expanding our Azure Quantum Compute platform across a variety of hardware providers. So thank you so much for coming to learn more about the work we're doing together, and enjoy your quantum journey for the rest of QWC. Thank you.